So far we've only done confidence intervals on the population mean, or true mean. Now we're going to turn our attention to confidence intervals on the true variance. Right, that's to be differentiated from a confidence interval about the true mean with an unknown variance that led us to the t-distribution. Right? Here, this is truly now about the variance itself. So because we've switched what measure we're actually looking at, let's go back and be a little bit formal here. That x is our random variable that's being drawn from a normal population with some mean and some variance or standard deviation. Right? And then we have a random sample, x1 through xn, that has a sample mean and sample variation. Okay. Before we pull the random sample, these are variable quantities. After we pulled x1 through xn, now these are deterministic. They're known. Maybe not calculated yet, but they're, quote, known at that point. And we want to use those to somehow, in this case, give us a confidence interval associated with the true population variance, or this guy right in there. Right, so what we're going to do is we're going to define yet a new statistic that is x squared, that's defined to be n minus 1 times s squared, that's capital S squared, over population variance. Right, and this is really not x, this is actually a chi, hence why this is going to come from the chi squared, that's the Greek symbol chi, lowercase in that case, with n minus 1 degrees of freedom. Now back in chapter 3, as part of your reading, chi-squared distribution came up, and I said, hey, later on this will come back, but we're not going to focus on it right now. And here you go. Here it is, and you'll see that it has interesting relationships to the gamma distribution and some of the exponential values that you see in terms of its actual mathematical description here. But one of the things I want you to do is really just have a sense of the kind of shape that we have. So let's go back to our text in one of the figures. That figure being figure 8.8 in your text. And so note that we've got three different curves plotted, and that they each have different degrees of freedom. Here's k. Right, so with k equal to 2, we have a highly asymmetric distribution. Really looks like the exponential distribution, right? K equal 5, then we get this little mounding feature, and then it tails off. And then at k equal to 10, this becomes more and more normal-like. And so as k goes infinity, we can expect this kind of transition to continue on. But a couple of key properties that we want to keep in mind here. Again, it is an asymmetric distribution, and because of that, the upper and lower bounds from a confidence interval standpoint are not going to be just plus and minus values of each other. That'll be a crucial aspect. Also note that by the very nature of it being a squared value, its domain is non-negative. It doesn't go to minus negative infinity, it goes from 0 to positive infinity. That's going to ultimately always make it a little bit different than the normal distribution. So let's go back here to the figure in the book. this tiny little version of figure 8-9. The details here aren't so critical. It's that I want you to note that in this chi-square distribution, when we're pulling out these bound values, this is a one-sided version here, and then we've got one here and here. Once again, note, we'll talk about where this number comes from. There's a 3.94 over here and an 18.31 over there. These are not plus and minus values of each other. We have to go, if we want a two-sided interval, we have to go into the table twice to get this number and then that number. And noting that it turns out this alpha value is going to be up here in this upper tail, and that's going to mean something kind of interesting here in a moment as we go about getting this confidence interval. So let's revisit our fatigue data. Let's revisit our fatigue data and note that our sample mean was 26.75, our sample standard deviation was 20, and we had 16 data points, right? And we're going to go after a 95% two-sided confidence interval for our variance. Right? And so if that's the case, then we're going to be looking at an alpha over 2 value of 0.025, right? Two-sided, area out in the tails being divided equally, and then n minus 1 is going to still be 15 like we did before. Right, and a 1 minus alpha over 2 would be a 97.5. And the way we go use this table for chi-square is similar to, but a little bit different than what we were doing previously. And so now note that in table 4 of your text, right, page 710, that notice that our alpha value that they're showing us here, this area that's sitting out here, is to the right. So that means we have the 1 minus the cumulative that's at work here. That's a critical thing in how we read this. So we still have nu as our degrees of freedom, and there's our alpha value, the area that's sitting out here. For two-sided 95% confidence interval, that number is going to be 0.025. So we're going to come over here to 0.025 to the right of that number. We also had one that was going to be 0.975 to the right. Right? We cannot use just the plus or minus values here. We have to go in and do this twice, and we'll go down to where our degrees of freedom are located, and we get a 6.275 and a 27.49. So 6.27 and 27.49. Okay, so we went into our table. Our chi-squared value for 0.025 and 15 degrees of freedom was 27.49. And our chi-squared value for 0.975 and 15 degrees of freedom was 6.27. Now this will temporarily look kind of goofy because this looks like the lower upper, or what, wait a minute, what? What's going on here? Right, so before we go chug numbers, let's go back here just a sec and formalize, wait a minute, how are we going to get this two-sided thing? What is this really looking like? two-sided for the variance, and we're trying to come up with an interval for the variance here. And so we'll have n minus 1 times our sample variance that's been calculated, and then chi-squared alpha over 2 n minus 1. Now this looks goofy. This was actually the right tail, but we think of that as high numbers, but that's going to go in the lower bound. And that'll seem goofy, but once we do this calculation, that goofiness will go away. And then over here on the other side, then we get the chi-squared and the 1 minus the alpha over 2 and n minus 1 degrees of freedom. And of course, the reason why is because the chi-square is sitting down in the denominator, so the larger number is actually going to create then a smaller bound over here. Right, so let's do this a little bit in parts. N minus 1 times s squared is going to be 15 times 40 squared, times 20 squared, and 400 times 15 is 6,000. Right? And so that, when we put in 6,000 in the numerator, divide by 27.49, we end up with then 218 as our lower bound on the interval, and then on the upper bound we end up with 957. And note how wide this interval is. That's very large, much larger than what we had for the for the other one, for the true mean. Right now, wow, that's pretty darn large. Okay, let's say that we had n minus 1 equal to 100 instead. And so now we have a much larger sample size. What would happen to us here if that were the case? Well, then that would change our chi-square values to 74.22 and 129.56, and that would give us then 539 and 309 for our confidence interval on the variance, which, if we were to take the square root of that, would get us to 17.5 and 23.2 on the standard deviation, which is a little easier to kind of take a look at. But even there, note, that's still a pretty wide range. And it illustrates the real challenge here as we go up in order of the moments. We go from that first order moment, which is the mean, then we go to second order moment, which is associated with variance, and if we were then to go to skewness and then to kurtosis, our number of samples that are required in order to have fairly tight bounds on these measures are going to just explode on us. And so it becomes a real interesting challenge of how you're going to then go out even further and have a lot of confidence in the higher order moments. And so it lends itself to perhaps a different approach if you're really interested in these other higher order moments as you're going along.